Hi students, welcome to the video lecture 3 of heat exchangers. In today's class we are going to cover the topic is logarithmic mean temperature difference of parallel flow heat exchanger. In the short form it is called LMTD. It is logarithmic mean temperature difference. Consider a double pipe. See here, consider a double pipe parallel flow heat exchanger in which both hot fluid and the cold fluid flow parallel to each other, and these two fluids are separated by a solid wall. Hot fluid enters at a temperature of TH1 and leaves the heat exchanger at a temperature of TH2, which is shown in the graph here. Whereas cold fluid enters the heat exchanger at a temperature Tc1 and leaves the heat exchanger at a temperature Tc2. So when the hot fluid is flowing along the length of the heat exchanger, so heat transfer occurs across the walls of this inner tube. It is shown by the arrow mark here. You can see heat transfer occurs from the hot fluid to the cold fluid across the walls of the inner tube, which is shown by the arrow mark here. So when it is flowing along the length of the heat exchanger, this hot fluid, it gives up the heat to the cold fluid, whereas the cold fluid, it gains the heat which is given from the hot fluid. Let TH1 be the temperature of the hot fluid which is entering the heat exchanger, which is shown here. So the temperature of the hot fluid, it goes on decreasing along the length of the heat exchanger. See here the graph, we can see here the temperature goes on decreasing here, whereas the cold fluid, it is gaining the heat. It is gaining the heat which is received from the hot fluid, so its temperature goes on increasing when it moves along the length of the heat exchanger. You can see here the temperature increases of the cold fluid. So the difference in temperatures of the hot fluid and the cold fluid at the inlet of the heat exchanger, it is given by delta T1, whereas the difference in temperatures of the hot fluid and the cold fluid at the exit of the heat exchanger is given by delta T2. Here our main desire is to get an expression for the rate of heat transfer for this parallel flow heat exchanger. It is in this following form, that is Q is equals to U into A into delta Tm. So our main aim is to calculate the rate of heat transfer for this heat exchanger. But already we know that U is overall heat transfer coefficient, A is the area of heat transfer, where delta Tm is the mean temperature difference between the hot fluid and the cold fluid. So before deriving the equation, so let us make some following assumptions. So first one, this overall heat transfer coefficient is constant throughout the length of the heat exchanger. This is first assumption. Second one, the properties of the fluids such as specific heat of both the fluids are considered constant with temperature, and here heat exchange takes place only between the two fluids, that is hot fluid and the cold fluid. So there is no loss of heat to the surroundings. Practically there are the heat losses to the surroundings, but here we are not considering them. Here we are considering only the heat exchange takes place between hot fluid and the cold fluid. There is no loss of heat to the surroundings. Now Let us consider an elemental area dA of the heat exchanger. So let us consider this as the elemental area dA of the heat exchanger. So this dTH, it indicates the difference in temperatures of the hot fluids. So the temperature of the hot fluid, it goes on decreasing like this way. So at this point one temperature will be there, at this point again there will be decrease in temperature. So the difference in that temperature of the hot fluids, it is indicated by dTH. So similarly at this point the temperature of the cold fluid will be at one point, and here the temperature of the cold fluid will be different. So the difference, it is indicated by dTC, that is difference in temperatures of the cold fluid. So for this, let us consider an elemental area dA of the heat exchanger. So for this elemental area, let us write an energy balance equation. It is heat given up by the hot fluid, that will be equals to heat received by the cold fluid. So let me write the equation for this heat given up by the hot fluid, that is dQ. Why we are writing here dQ? Because we are writing this heat transfer for this elemental area dA, where dQ is given by mH into Cph into dTH. So this is the equation of the form where Q is equals to M into Cp into delta T. The same equation we are using here. Q is equals to M into Cp into delta T. The same equation I am writing here. That is dQ is equals to mH into Cph into dTH. The same equation I can write it for cold fluid also, where dQ is given by mC into Cpc into dTc. So we will put the negative sign in front of this equation, because the temperature of the hot fluid, it goes on decreasing when it moves along the length of the heat exchanger. So in order to make the heat transfer a positive quantity, so here negative sign is introduced here. So now next, this dQ, the heat transfer for this elemental area dA, I can also write this dQ in this following form. In this form also I can write it, that is U into dA in the bracket TH minus TC. The same equation I have used here, where Q is equals to U into A into delta Tm. This is the equation for the total heat exchanger, heat transfer. So this equation I am writing it for only the elemental area, for that purpose where U overall heat transfer coefficient will be constant only. So A is replaced by here dA, because I am considering only the elemental area dA, where that is difference in temperatures between the hot fluid and the cold fluid, that is TH minus TC. Let me call this equation number 3, this as equation number 2. So now from equation 2, I can write dTH will be equals to minus dQ by mH into Cph, whereas dTc is given by dQ divided by mC into Cpc. This mH indicates mass flow rate of the hot fluid, where M indicates mass flow rate, where subscript H indicates hot fluid, where mH indicates mass flow rate of the hot fluid, and Cph, it indicates specific heat of the hot fluid. Similarly, where mC indicates mass flow rate of the cold fluid, and Cpc indicates the specific heat of the cold fluid. So now from this equation only I can write this equation dTH minus dTc. This equation minus this equation dTH minus dTc, that will be equals to minus dQ divided by mH into Cph minus dQ divided by mC into Cpc. So minus dQ I have taken it as common outside. So in the bracket this will be 1 divided by mH into Cph So as our term, it should be negative here. So already I have taken minus sign as outside. So here it will be plus 1 divided by MC into CPC. The same equation I have written in this format. I have taken D outside, T of H minus TC minus this DQ value. I will substitute that from equation 3. In the equation 3, where DQ is given by U into dA in the bracket TH minus TC, minus sign as it is, this DQ value I have substituted from equation 3. It is DQ is given by U into dA in the bracket TH minus TC. TH minus TC means temperature of hot fluid minus temperature of the cold fluid, and this equation remains as it is. Now this TH minus TC term I will take to this side, the denominator. I have written the equation D of TH minus TC divided by TH minus TC. This equation I have taken here, minus U into dA. The equation remains as it is, that is 1 divided by mH into CPH plus 1 divided by MC into CPC. So let me call this equation as equation 4. Now integrating this equation 4 between the inlet and exit of the heat exchanger, that is between conditions 1 and 2. So this condition, that this limit 1, it indicates inlet of the heat exchanger, whereas limit 2, it indicates outlet of the heat exchanger. So if I integrate this equation between the limits, that is inlet and exit of the heat exchanger, so I am going to get this term. So if I consider this TH minus TC as X term, so then this equation becomes dx divided by x. So that is integration of dx by x, that will be log x. The same equation I have written. Then with the limits 1 is to 2, if I apply here, then I am going to get this term log of TH2 minus TC2 divided by TH1 minus TC1, that will be equals to minus U. So even here also this U term and these terms becomes constant. So integration of dA with the limits a equal to 0 to a equal to a, so integration of dA will be a only. So this equation remains as it is. It is 1 divided by mH into CPH plus 1 divided by MC into CPC. Now considering the total heat transfer for the entire heat exchanger. So previously we have written the equation of heat transfers only for the elementary area dA. Now considering the total heat transfer for the entire heat exchanger. So for the entire heat exchanger, where Q indicates the total heat transfer, so if I want to write the equation total heat transfer of the hot fluid, so this is given by mH into CPH, the bracket TH1 minus TC2. The same equation again, that is M into Cp into delta T. That equation only I have used here, where Q is equals to mH into CPH in the bracket TH1 minus TH2. This is for hot fluid. Similarly, we can also write this equation for the cold fluid also, where Q is equals to MC into CPC in the bracket TC2 minus TC1. So here you can see here TH1 minus TH2 we are written here, because the temperature of hot fluid at the inlet will be more than the temperature of the hot fluid at the exit of the heat exchanger. Here the temperature of the cold fluid at the exit of the heat exchanger will be more than the temperature of the cold fluid at the inlet of the heat exchanger. For that purpose here we have written TC2 minus TC1, because this temperature is greater here. Now by these equations only, by these two equations only, I will write the equations, that is mH into CPH will be equals to Q divided by TH1 minus TH2. So this mH equation I have written this from this equation. Similarly MC into CPC, this will be equals to Q divided by TC2 minus TC1, based on this equation I have written here. Now substituting these mH into CPH value and MC into CPC value in the previous equation, that is equation number 5. So this term as it is, this is log of th2 minus tc2 divided by th1 minus tc1 minus ua. I will write as it is only, and if I will substitute the values of mh into cph, so in the equation 5 it is 1 divided by mh into cph. So 1 divided by mh into cph I will write in this form, that is th1 minus th2 divided by q. 1 divided by mc into cpc. So if it is 1 divided by mc into cpc, then this term will become tc2 minus tc1 divided by q. So in both the terms q is common, so I have already taken q here outside, minus u into a divided by q in the bracket th1 minus th2 plus tc2 minus tc1. Now next equation, log of the bracket th2 minus tc2 divided by th1 minus tc1, the same equation I have written here. So here I will multiply each and every term inside by minus sign for these equations. So if I will multiply with minus sign, so this becomes minus into minus, plus this becomes plus th2, this becomes minus tc2, this becomes plus tc1, then this becomes again minus th1. So ua divided by q. So I have rearranged the terms. I have written here th2 minus tc2. th2 minus tc2 minus I will take outside th1 minus tc1. So if I will remove these brackets, so my equation will be in this formula after multiplying this equation with minus sign, ua divided by q. Now with this equation, let me write the equation for q here, where q is equals to u into a in the bracket th2 minus tc2 minus th1 minus tc1 bracket complete divided by log of th2 minus tc2 upon th1 minus tc1. Now comparing equations 1 and equation 6. So if I will compare, so in the equation 1 it is q is equals to u into a into delta tm, whereas equation 6 is given by q is equals to ua and the entire term. So if we'll compare the equations 1 and equation 6, so easily I can write this delta Tm will be equals to Th2 minus Tc2 bracket complete minus Th1 minus Tc1 whole divided by log of Th2 minus Tc2 divided by Th1 minus Tc1. So now delta Tm is equals to this Th2 minus Tc2 is replaced by delta T2 and Th1 minus Tc1 is replaced by delta T1, because in the sketch only we have already explained here the difference in temperatures of the hot fluid and the cold fluid at the exit of the heat exchanger is given by delta T2, which is shown in the sketch, the graph. Whereas difference in temperatures of the hot fluid and the difference in temperature of the cold fluid at the inlet of the heat exchanger is given by delta T1. Similarly, divided by log of this term is replaced by delta T2 and this term is replaced by delta T1. Let me call this equation as equation 7. So as this temperature difference, it varies in a logarithmic manner. For that purpose, this delta Tm, it is replaced by LMTD, logarithmic mean temperature difference. This will be equals to delta T2 minus delta T1 divided by log of delta T2 divided by delta T1. Or the same equation I can write LMTD is equals to, in this way also I can write delta T1 minus delta T2 divided by log of delta T1 divided by delta T2. So this is the derivation about the LMTD, that is logarithmic mean temperature difference for parallel flow heat exchanger.